We've been talking about performance, and now we're going to discuss some structural aspects of aircraft design. We've kind of saved this topic till a bit later, even though for a normal aircraft, structures is kind of a primary consideration you want to consider up front. There's often, in particular, significant trade-offs between aerodynamics and structures. For the airplanes that you're designing and building, the loads are very small, and so the structural loading is not as important. And so we've kind of saved it till later so we can move some other topics first. But just keep in mind for large airplanes, this is often a primary consideration. There's kind of three things we want to discuss today. One is get a basic understanding of aerospace structures, aircraft structures, what they typically look like. And the main loading we're going to look at is a wing. Okay, so for a wing, there's a lot of this bending stress that occurs from the loads on a wing. That's where, of course, almost all the lift is generated here on the wing. So we're going to look at how does that change the design, and specifically when we look at thickness of the airfoils. You may think about, do we want thin airfoils, thick airfoils? What are some of the design trade-offs there? And lastly, we're going to revisit an ideal lift distribution. You'll recall when we talked about induced drag that we saw that an elliptic lift distribution was ideal. And again, that was just for induced drag standpoint from a fixed span. But if we think about structures, we'll have to revisit how does that change things, okay? Just give me a second here. I'm going to share my screen. All right. Here's an example of an interior structure for an aircraft. What you may notice is a structure which is called a semi-monocoque structure. So a monocoque, this is a French term, which means that the structure is provided through an external skin, okay? And a classic example, that would be an eggshell. All the structures is provided by this skin. It's, on the outside, a semi-monocoque uses that skin, but has these generally for these cross members, right? These compressive structure members. So you're gonna have the skin that's in tension, and then these compressive members, that will give some terms to ribs, frames, longerons, and things that carry a lot of the compressive loads. And you can see that in the picture. You can see the outer skin, these compressive members, and the reason why this is used is that especially for aerospace structures, is that it provides a lot of strength for little weight. That we can really reduce the weight of the structure with these kind of configurations. Here's an example for a fuselage type structure. Notice we've got the frame in blue, and there are many of those. So there's going to be one of these sections. You can see some of them throughout. And so you might ask yourself, what is the purpose of a frame? Think about that for a sec. And there are more than one. Perhaps a more obvious one is that it provides the shape. Right? As I change the frame, that's going to provide the shape as the skin goes on the outside. Another maybe less obvious one. Notice all these cross members. What would happen if I have frames that are further apart, so fewer of them, as compared to many frames which are close together? Well, if they're far apart, then those red structures have longer sections before they're supported. And so what kind of challenge is that going to occur if I've got these long sections that are supported at further distances as compared to short? That's going to really affect my buckling strength, right? So if I have lots of frames, of course, that's going to maybe cause more weight. I'm going to have greater buckling strength because I'm supported across shorter distances. These stringers or longerons, often these are used interchangeably. Historically, there's some subtle differences in what they mean, but we're not going to go into that. These are long, these are these numbers that are going to run along the length here. These are going to carry a lot of these longitudinal loads, okay? And then the skin here, again, it's going to provide, sort of this outer aerodynamic shape, but it's also going to carry some of the torsional loads and shear loads. A wing is going to have a very similar type of structure. In green, again, this is a rib instead of a frame, but a similar type of idea. One, that it provides the shape. You can see it's going to have that airfoil shape. So it's going to be periodically we're going to have another one of those. It's also going to similarly increase my buckling strength as I have more of those, so I don't have these long members. I've got these stiffeners in red, similar to those longerons, going to carry some of those longitudinal loads. A difference here in a wing is that in the wing, we're going to carry a lot of load from the lift, right? It's going to cause my wings to bend. And so I need both what are called a spar cap, and that's the skin, this area in the skin. Let's highlight here, kind of between the spars, up and down. That's where a lot of the bending stress is going to be carried. These spars are also going to carry some of that vertical load, but what else will the spars do? Imagine I don't have the spars, I just have this vertical section. If you remember from structures, that's going to really increase my torsional rigidity, so that's going to help me with torsion. So those are going to help stiffen that up. Sometimes in other applications, these will be called shear webs, but similar concept here. Okay, so this is a typical wing structure might look like. Let's look at the loads on an airplane. Now imagine that, we've talked about being in a steady flight where lift equals weight. So that just means that the net lift and the net lift, the total force, right, are equal, but that says nothing about what the distribution looks like. And here's maybe what a distribution might look like. Lift distribution, it looks somewhat elliptic as we've talked about, but because of the fuselage presence, fuselage isn't going to be as effective as the wing to generate lift. There's generally going to be a drop in lift here. And for these transport aircrafts, most of the weight is going to be concentrated in the center. Of course, there's some peaks, local peaks where we have these engines. But, all of the cargo, people, all the storage, all that stuff is going to be here in the center. So we're going to have a lot of weight concentrated in the center. So if you think about this, what are the primary stresses that are going to occur? Well, a big one is going to be the bending, right? Because the inertial loads, those weight loads, are all towards the center. They don't provide much of the moment, but my lift is distributed way out there. So I'm going to have this sort of net bending moment, wanting to bend my wings up as I load this up. Especially if I need to do a maneuver and I need to increase my lift above my weight, say so I can do a turn or whatever, that's going to bend my wings further, okay? And we'll see a video of that in class, but here's let's say there's a picture here of that bending moment. So again, imagine my wings are bending. Which side is in compression, which is in tension? Well, if my wings are being bent up, right, as will be normally the case for a 1G flight or higher G, this top surface of the wing is in compression, this bottom surface is in tension. That's what's depicted here on the right. This moment is pushing on the top compression, tension here on the bottom. So I've created this bending moment and this airflow, right? It's just a slice. We often will picture an airflow structure this way. These are those spar caps that we saw, and then the skin is going to be much thicker here. These are often called spar caps in between here and here. There's generally very little structure. So this is what's called a box beam structure. So it looks like a box, and it's going to extend along the wing like a beam. Along the trailing edge and leading edge, there's very little structure. It's not carrying loads, it's just for shape. So for structurally, we just need this kind of shape, but aerodynamically, of course, we want an airflow shape. So we need a thin skin to provide that shape, but it's not going to carry any loading. And again, you might see this if you look out the window sometime when you're flying. You might see on top of the wing these painted lines, and then an area here that says, I'll say something like no tread, or you don't walk there, because if you drop tools there, you walk there, right? It's just a thin skin, maybe aluminum or something. Depending on the airplane, maybe the new one will have more composites, but that's going to be something you want to walk on. All the structures here, that's where you can put the weight. All right, so let's break this down here. And before we do that, what I want you to think about, if we look at this airfoil, from a structural point of view, is it going to be advantageous to have a thick airfoil or a thin airfoil? What is going to save me more weight? I got to resist the bending loads, of course, but assuming I can resist those loads. So I want to have a thin airfoil to reduce weight or a thick airfoil. Just take a little bit, a few seconds to think about that. And let's work that out after you thought it through. So you may remember from your structures class, what is the stress from bending? What does that look like? Sigma equals my over I, right? So m is the bending moment, y is the distance from the neutral axis, and I is the bending moment about that neutral axis. So in this case, that's going to be an axis somewhere around here in the middle. So y is going to be like, say, half the thickness of the airfoil, approximately. To make a calculation, let's simplify this. Let's consider this box beam as just rectangles on the top and bottom, and we'll ignore the sides. And the reason we're going to do that is because their contribution to the moment of inertia, this I, is going to be pretty small, right? So y is just going to be this t over 2 bending moment we have, and I we're going to approximate as these two rectangles. We could do as the box, but again, most of that is going to be close to the center where it doesn't contribute much moment of inertia, okay? So this is a common sort of simple model. And now we want to look at what is the mass of the structure that we need, okay? The mass of the structure, we could integrate. It's going to be this area, and there's half the area up top, half the bottom. We're going to integrate that area. It can be different at every airfoil section along the wing. So we integrate that area. If I didn't have density, right, this integral will just be a volume. So we're going to multiply by the density of material, which potentially could change as well as it's under the integral. This is the mass of material I need. So if we take these two equations and we assume this case where, let's say, every section is as efficient as it can be, meaning we didn't put any extra material more than we just barely needed. So let's say we're right at the yield stress. And of course, this is a simplification because we're only considering bending, and really we'd also consider, shear, torsion, the other loads that are on your plane. But say just bending, we're right at the limit of just yielding. So we could solve this, we put in what I is in terms of A, right? Moment of inertia in terms of these areas. We solve this for A and plug it in. What we're going to find here is that that mass is proportional to the bending moment over the thickness. Now the bending moment in the numerator should be intuitive, right? As I increase that bending moment, I put bigger loads out there, right? Increase the bending moment. I'm going to need a heavier wing to carry those loads, right? Because the stress is going to go up. So I'm going to need beefier areas, right? These sections are going to have to get bigger to carry that stress, so I don't exceed my yield stress with the safety factors. And so the mass is going to go up. Perhaps less intuitive is that the thickness is in the denominator. What this means is that I actually am going to have can have a lighter structure if my airfoils are thicker. So in general, a thicker airfoil is going to allow me to save weight. That seems a bit counterintuitive at first, but the reason here, right, as we look at this, is that as I increase thickness, what happens to my moment of inertia? Imagine I bring thickness in really small versus really large. If the airfoils are really thin, my thickness is small, my moment of inertia is really small, right? And that means I'm going to have bigger stresses, or in other words, to compensate, I need to put a lot of material in these areas to get those stresses down, to get the moment of inertia I need so that it's more resistant to bending. Whereas, or in contrast, if these were further apart, then I don't need to put as much material in this cross-section to make my moment of inertia large enough to carry the stresses that I need. So by having thicker airfoils, I can put material further away from that neutral axis, and I don't need as much material there to carry a given level of stress. So I can actually reduce my weight. And this is maybe one of the fundamental tensions between aerodynamics and structures. Typically from a drag perspective, right, we'd like thin sections. Of course, there are limits, and there's some aerodynamic reasons to have a bit thicker, right, for like CL max and things. But generally speaking, there's a primary trade-off between thin sections, which are going to be, more aerodynamic, as we might say, roughly. In other words, they're going to have less profile drag because we don't have to displace the flow as much, right? So a thinner section is going to be better, generally speaking, for aerodynamics, whereas a thicker section, again, generally speaking, is going to be better for structure. So this is going to be one of those trade-offs that we'll need to look at. Okay, so another thing we're going to want to look at is what that lift distribution should look like. We've mentioned elliptic. This is a nice idea. And I should say before we move on, this analysis here is for, this kind of a very common sort of fuselage tube and wing type concept. But if you've got something different, like say a flying wing, then the weight tends to be much more spread out. And this analysis may not apply, right? Because this inertial loading may be very similar to the aerodynamic loading, and you actually may not have very much bending loading. and other considerations, like say for example, a dynamic load like a flutter may be much more critical, for example, than this for static bending. With that aside, let's go look at a lift distribution and try to figure out what's ideal from a structure standpoint as well as aerodynamics. So to do this, first we're going to look at a simple metric, root bending moment. Root bending moment is just what's the bending moment. So here's a lift distribution. I'm just looking at half the wing because it's symmetric. What's the bending moment here at the root of the wing? This is a simple metric. It's not a very good one because, for example, it totally ignores like the thickness. We just talked about how thickness of the airfoil is important. And I could change this thickness all day. And for this given lift distribution, it'll have no effect on root bending moment. So it's not really a good model per se. It's also not good for non-planar wings. It's just kind of a contrived example. Let's say I added a winglet, and if I just turn the winglet so that the load was exactly pointed towards the root, we would say, oh, it contributes nothing to the root bending moment, right? Because the moment arm is 0. But of course, that had to have added some weight, right? And it's adding loads and bending stress. So it's not really a good example or a good metric in general, but it's a good motivator of, let's say, the primary physics here, what's happening, at least for this conceptual discussion. So what is root bending moment? From this, well, it's just an integral, right? Now this is a distributed load. So let's say I've got my force and I need to multiply by a distance. So it's just this coordinate here for a wing, we generally call this y. So I'm going to multiply by that distance. And L prime, of course, is the force per unit length. So I need to integrate this across my wingspan, say 0 to b over 2, right? Because that's b over 2 is, this is half the wingspan because we're just looking at half the wing. That's my bending moment. And I think I already looked at this on the next slide. So, okay, so there it is. All right, so you'll remember from statics, another way we could look at this is that we can always represent our distributed load as a point load. And of course, that could come with a moment, but if we put it at the center of the loading, the center of that loading, then, we can, it'll just be a point force at some location, okay? We don't know where that location is per se because we haven't said what L prime is. It's just any arbitrary lift distribution, but we know that the total force is L over 2, right? And since this distance here is B over 2, we're going to say this distance is eta times B over 2. Eta is an unknown. I don't know what it is yet, but it's something between 0 and 1, right? So basically what we're saying is we could, one way to represent our lift distribution is, or we could talk about it, is where is that lift centroid, the center of lift there. And from a structural perspective, the question is then, what's ideal? What would we like that lift centroid to be? Well, let's think about it. If it was very large, is that good for our structures? If the lift centroid is really far out, that's not ideal, right? Because that means the bending moment acting on my wing, or specifically the root bending moment, is very large, right? In general, we would love eta to be really small as possible. Of course, we can't make it too small, it's bad for other reasons, but from a structural perspective, if it was really close to the center, then I've got, very little to no bending moments, and that's great. And I can have a very light wing, at least from a bending stress perspective. Okay, so that's the structural desire, of course, is that we want eta to be as small as possible. But what about from an aerodynamic perspective? What about from an induced drag perspective? We said we want an elliptic lift distribution. What does that correspond to? Where an elliptic lift, or so in other words, for an elliptic lift distribution, what is eta? So here's a plot of this equation. I think this is derived by Archie Jones. So this is what E inviscid, remember what E inviscid is, that's that inviscid span efficiency, which for an elliptic lift distribution V1, that would be the maximum we could get for a planar wing, so that would be the best for induced drag. Remember again, induced drag was, or the coefficient, actually let me just write the full drag here. Lift or dynamic pressure, B squared, and then the inviscid component. And then later, remember we changed that to the Oswald efficiency when we added the viscous component. But just thinking about the inviscid component of induced drag, okay? So we want that denominator to be as big as possible. We'd like it to be 1, that's gonna be elliptic. Well, what this equation here says is for a given position of eta, what is the best you could do? It doesn't say what you will get, because if I just told you what eta is, let's say I said eta is 0.3 or whatever, there's an infinite number of lift distributions I can create that have eta at 0.3, right? I can shift things around so that the centroid is at the same place, but looks very different. But of all those infinite combinations, what's the best I could do from a drag perspective? That's what this equation tells me. So what it says is, one is elliptic, that if my lift centroid is at 4/3 pi, then that would be ideal. Like, then I could achieve elliptic. Again, that doesn't mean that if my centroid's at 4/3 pi, it's automatically elliptic, but it means it could. That's the best I could do, is to get one. I could get elliptic. Or in other words, an elliptic lift distribution has a centroid at 4/3 pi. And that's, what is that? Let me calculate that real quick. I think it's like 47, or 42, 42.4%. So in other words, an elliptic lift distribution has its center of lift a little over 42% away from the root. So we've got this tension here where I'd like to, from an aerodynamic perspective, keep my center of lift somewhere over here. But from a structure perspective, I want my center of lift to be as far to the left as possible. So what this suggests, though, is that we're going to, as in all things in engineering, we're going to compromise. The compromise is the best solution because our objective is neither drag nor weight. It's something higher, right? Like, say, some sort of fuel burn or operating costs or net present value or, net whatever that we want to optimize for, that's going to balance some trade-off between aerodynamics and structure. So we don't want the minimum drag or the minimum weight. We want something that combines these in some balance that's best for the whole system. So if we look at this figure, just like any optimum, remember again, the definition of the optimum is that the slope is 0, so it's very flat. That means that if we don't change it too much, if we go off a little bit, we won't lose very much E inviscid, right? This curve is going to be pretty flat, but we could change eta, a decent amount without having to change E inviscid very much. And that's exactly what happens for an aerostructural optimum. Here's an example. Right, here's aerodynamic optimum, which is elliptic in blue. And often what's going to happen is that the aerostructural optimum is going to shift the load inboard a bit, right? So it's going to bring that lift centroid in a little bit. So I'm going to carry more load up here than towards the tip. That's going to reduce my bending stress, and that's the weight I need. And it's going to have a small impact on my induced drag, but because it's flat at the top, it's not going to be too significant. So just for reference, a typical value might be E inviscid of about 0.98. Meaning I didn't go all the way to the best I could with one. I gave up a little bit. 0.98 isn't much, but it allowed me to move my lift centroid significantly enough that my bending stresses have come down. One thing you could do with that, which is depicted here in this picture, is I could keep the same span, just move that in and have a lighter wing, or for a given stress, say I wanted to keep the stress the same weight, I could bring that lift centroid in, which would then mean I could increase my span and still have that same bending stress. And I could bring that span out, so now you can see there's an even larger span. And that would actually reduce my drag even more, because even though E inviscid went down a little bit, by increasing my span, that extra amount for the same stress, I actually reduce my drag even further, because there's a span squared in that term. So the aerostructural optimum, in general, whether you increase the span or not, right? Like, it depends. Do I want to hold my weight constant or stress constant or whatever, right? Or a fixed span. Either way, and again, this shape will vary, in different ways depending on what the weight metric is, right? Is it just looking at bending stress? Are we using an integrated bending moment or thickness? Are we considering multiple load cases? There'll be subtle differences, but the important consideration or the important takeaway here is that once we consider structures, generally we're going to shift our load inboard. We're not going to use this perfectly elliptic lift distribution. We're just going to shift it inboard because it's a small compromise to aerodynamics, but allows us to save weight on our structure. And again, for your wings, where you've got these solid foams with low loads, these are, more minor considerations, right? These are not, they become more important if you do like a built-up wing. You want to get a really light wing, you could do something very similar, and many model aircraft enthusiasts do this. They'll make a monocoque type structure, right, where you just build up the ribs and you cover it with a thin film of kind of this plastic wrap called monocoque, or this is the brand name, and then you can get a very light structure that can be very efficient. So to recap, kind of the two main takeaways, besides sort of a picture of what these structures look like, these semi-monocoque structures, is that a thicker airfoil will actually can save weight for a bending constrained airplane, that is, which is typical of many designs. And then in general, we'll actually shift our lift distribution inboard rather than keeping it elliptic. We'll kind of bring it in order to get either a lighter wing, or for a fixed weight, we can actually reduce drag by pushing things out. So thinking about it in a multidisciplinary context means that we usually go a little bit inboard of elliptic. Next time, we're going to talk a little bit more about structures, thinking about loads, flight envelopes that an airplane is going to fly in.